I would like to acknowledge the Wurundjeri people, who are the traditional custodians of this land. I would also like to pay respect to the elders both past and present of the Kulin Nation, and extend that respect to other Indigenous Australians present.
Our speaker today is Simon Dennis, and I'll just pass it over to you to let you introduce what you're going to talk about.
Okay, thank you very much. So first thing I want to say about this talk is that it's definitely a work in progress and has been since about 1983. So hopefully shortly we'll get to this. So what I'm going to talk about today is a model of sequence generation. And so this is kind of quite topical at the moment, something I've been interested in for a long time, but it's quite topical at the moment because we have, okay, there we go. Because we've seen a bunch of new models of sequence generation that have been getting a lot of hype recently. And so one of the dominant ones is GDP3. And so this is an article hyping up GPT-3, but you'll see many such articles around and claims about its capabilities. There was a Google engineer who was fired for claiming that GPT-3 was sentient. It's now writing about 40% of the code for people. So GitHub has this Copilot capability and that you can insert into your coding environment, and it's actually writing significant proportions of people's code using it. So it's quite capable, but there's also a lot of hype. Now, what's particularly interesting about this article that you see in front of you is that it wasn't written by a person. It was actually written by GPT-3. And so you can see, right, that it's pretty coherent, and that's why people have become so excited about the model. So to give you, beyond examples like that, it's also been used for a number of different tasks. So here's just a few simple ones from a blog post by Lacquer. So these are queries and answers. So the query was given by the human, and then the answer was given by GDP-3. And so what's my favorite what's your favorite animal? My favorite animal is a dog. Why? Because dogs are loyal and friendly. What are 2 reasons that a dog might be in a bad mood? So it gets that. How many eyes does a giraffe have? Gets correct. How many legs does a frog have? Are there any animals with 3 legs? No, there are no animals with 3 legs. Why don't animals have 3 legs? Animals don't have 3 legs because they would fall over. So it's capturing, a lot of kind of interesting structure, a lot of kind of common sense knowledge. Just a few more examples. So which is heavier, a mouse or an elephant? So it knows the elephant should be heavier. The toaster is heavier than the mouse, gets the pencil wrong. But it gets a lot of these kind of common sense facts correct. Okay, and so one of the key interesting things about these examples, right, is that it's just trained on text, and so it has no other experience other than the text that it's exposed to, and so it's deducing all of this from the corpus. Just to give you a couple of other examples, so this idea, one of the things that's key about this, right, is that the kind of control architecture of the task is built into the input that the model is being given. Okay, so this is what is kind of commonly referred to as kind of few-shot learning. And so I've been advocating this kind of idea for some time. So I wrote a paper in 2005 where I presented a model that was capable of this kind of few-shot learning. And the examples that you see here, though, are some of the structures that I presented in that paper, but presented to GDP-3. So here, these are ones that Kevin generated. So study the following list, condo 10, etc. The bot says, okay, now remember the words, and it's able to produce those words, right? And so the key thing here, right, is that this is not a model of serial recall. This is just a generic model of sequence production. Similarly, other examples I was interested in 2005 were looking at the way, how could it kind of capture this kind of question answer and be able to extract the relevant parts of a statement in order to answer. So, so the model that I presented then could do that, but so can GTP3. And so SpaceX sold the rocket to NASA. Okay, who built the rocket? NASA. So it's getting those kinds of things correct as well. Okay, and so that's important because it's capturing a kind of systematicity of the input. So, so I think the transformer models really are a game changer because up until now, right, there hasn't been a really large scale demonstration that the control architecture and the representational aspects required to work with that, that exists sufficiently in language to be learned, right? And so I think, a lot of people have, posited domain-specific learning modules with various different biases and so forth, or much further back in time, the language of thought as ways of kind of getting around this. And what GDP3, I think, is making much more plausible, at least, is that that's not really necessary, that the information exists. Now, that's not to say that people only get information from text or language, right? So clearly people get information from other places too. But the key underlying elements of the cognitive architecture seem to be learnable from language. And I think that's important. However, there are still many ways in which the transformer architectures differ from human language or sequence production. So one, they're learning very slowly relative to what people are, okay? So, an optimistic estimate of the number of words a person encounters in a lifetime is 100 million. GDP3 is trained with 43 trillion words, right? So that's about 100,000 times as much as what your typical person is exposed to. And the critical thing is that if it doesn't have that much input, it doesn't work. So, so it's not learning nearly as rapidly as what people learn. Perhaps even more important is that it forgets too quickly, right? So the basic underlying algorithm in the transformer model is the backpropagation algorithm. And we've known for a long time that these are not good models of memory, okay? So McCloskey and Cohen, 1989, presented this work on the ABAC paradigm. So in the ABAC paradigm, what happens is participants are trained on a list of pairs of words, which are the AB words, and then they are trained on a second list of words where the first words are retained, so you get the same set of first words, but they're paired with a different set of words. So those are the C words, okay? And so if you look on the left-hand side, that's what human performance looks like. So that's from Barnes and Underwood, 1959. And you can see, right, that as you get multiple learning trials on the list, performance for the AC list increases and performance for the AB list decreases. So that's retroactive interference. But, it does so relatively gracefully, right? You don't see a dramatic drop-off. However, if you look at what happens with backpropagation style algorithm, you can see that even after 5 iterations, the performance on the AB list is almost zero, right? And it takes quite a bit longer for the AC list to rise. So that's something that is a really fundamental difference between the nature of the learning mechanisms that transformer models are using and what people do. And if you think, oh, well, we're talking here about list learning and that's not really equivalent to kind of language learning. This was a study conducted by Mannering and Jones where they looked at the learning of word senses. Okay, so when you have a polysemous word like bass in this case, there's a fish sense, so it could be bass or it could be bass. And so there's the fish sense, and then there's the guitar sense, right, of the word. And so the underlying embedding model, which is word2vec in this case, and is word2vec's used in GDP3 as well, it kind of learns the representations of individual words. And so what they did here is they looked at what happens if you train the word2vec on just a normal corpus, as opposed to what typically happens, where they get the corpus and they randomize it, they mix it all up, right? So, so when you randomize it, right, the different senses then get mixed all through at different places in the corpus. But in reality, when you look at a real corpus, what happens is the words tend to appear in bursts, right? So you'll tend to get a burst of the fish sense and then a burst of the guitar sense in what people are actually experiencing. And if you do that, word2vec is also subject to this catastrophic interference, right?
I don't know, do you take questions?
Yeah, sure, go for it.
I'm just curious, I think this is really interesting, good demonstration, but is the context the determining factor when you look at least at kind of this catastrophic forgetting at the word level? Like the fact that you have GPT-3, it's not looking at these really short fragments, right? It's looking at this long context. Is that sufficient to avoid that kind of sense-related catastrophic
interference?
Yeah.
Well, it certainly has to be part of the story, right? How the context comes into it. The it's a kind of entering the context is a double-edged sword, right? Because on the one hand, in order to have the sense of the word, you kind of want that independent of the context, right? So that it can be used in a new context without having. So, but you have to kind of balance the context and the amount to which context influences, and it's a bit of a balancing act. Okay, but yeah, that's certainly that in the McCloskey and Cohen paper. That was Rumelhart. They talk about Rumelhart's objection to their work, and his objection was that maybe it could be related to context.
I mean, you probably don't see a lot of like sense errors in kind of the text and the language generated by GPT-3, where you can see now obviously there's like the sense of state.
But the thing is, right, the GDP-3 is trained on the word2vec. Like it starts with the word2vec embeddings, which are trained with randomized sequence.
But that's worth intriguing that it doesn't show those kind of sense problems in generating, like it wouldn't have that kind of bank.
Well, see, when you train with the interleaved training, right, then both senses can be represented to the extent that they actually, the proportion they're actually present in the corpus. Whereas if you trained word2vec through a corpus without the interleaving, the other senses would be gone from the embedding vectors, right? And so I don't think that the subsequent context is going to be able to reconstruct them to that point, because they don't even exist in the embedding. So anyway, it's maybe a discussable point. Yeah. And then I also want to point out that there's no known neural mechanism for the backpropagation algorithm. So so in order for transformer models to work and backpropagation models in general to work, you need error to be backpropagated from a signal that's at the outputs back through the network. And the transformer networks are very deep architectures. So the requirement is that error signal goes back all the way through the architecture. So there are two problems with that when you consider the actual neural hardware. So firstly, the signals that you're talking about are very noisy signals, right? So how's the value of the error signal? How is it actually maintained when you have these very noisy signals, right? But the second, and I think even more pressing issue, is how is it targeted? Because these deep architectures it's not good enough to say, there was an error up here, so therefore you need to change something down here. You need to trace that error all the way back through the network and make sure that it's proportional to all of the weights that are intervening, right? And there's, I think it's extremely unlikely that that's the mechanism that that's actually being used in the brain. So to say that another way, when you're optimizing using backprop, it's a direct optimization, right? So you have an objective function at the output, and the gradient is backpropagated to update the weight of a particular weight within the network, and the amount of update depends on the specific location of that weight. So that seems very unlikely. So what I think is more likely is an emergent view. So in the emergent view, the idea is that if you optimize locally the function that's being calculated at each of the nodes in the network, then there is an automatic guarantee of global optimization, okay, without you needing to actually propagate error or anything around the network. And so that happens in a Gibbs sampler, okay? So in a Gibbs sampler, you're, as long as you're correctly estimating the conditional probabilities at individual nodes, it's guaranteed that the entire Gibbs sampler will converge to the global joint posterior. And so, so therefore you now don't need any of these, action at to propagate through the network in order to make that the case. You just have to worry about being optimized locally. So I think that's the much more likely scenario, and that's what the model I'm going to propose does. Okay, so this is what the model looks like. And so the idea is that you have a series of slots at the input. And as you are either experiencing a text or trying to generate a text, those slots get filled with individual words or tokens, in fact. So, the most recent slot will be for whatever was the most recent token, and then you'll have slots going back for the tokens that appeared prior to that. In addition to that, though, the assumption is that there are connections to context. So each of all of those slots that are in this kind of, you might think of as like a short-term memory at the bottom, are all connected to a context which is integrated over a window, okay? And my assumption is that there are contexts of different widths, right? So here I've got 10, 50, and 400. I'm not really committed to those particular numbers. But the idea is that those contexts are now order independent, okay? So that what appears in that context is an element for every word that appeared in the last 10 words. Okay, it's basically the count of the number of times that word appeared in the last 10 words. So the contexts are multinomial distributions, the slots are categorical distributions. The model that I'm going to show you some generations from later is just the green bit. Okay, so I haven't added the longer contexts in yet. Key thing to notice about this model is there are no latent variables. Okay, so unlike what you'd see in a hidden Markov model or something like that, everything is just connected to everything directly, right? So every as you're learning, all of these elements can be filled in directly from what the text is that you're actually exposed to. So so you don't need to infer any latent representations. And so that then has the advantage, right, that it's a lot easier to learn because you're always just learning associations between things that actually appear in the input.
Are the contexts fully encoded? Like, do you assume that the contexts are perfectly remembered?
Well, these are things that have just occurred, right? So this is the last 10 items. Yeah.
But like in the 400s, if you'd go up to that.
Yeah, probably. I would say they're all there. Yeah. Like the connections, right, are the, what happened in slot 3 at this time connected to all the things that are 400 back, essentially. So you're not keeping the contexts as joint information, right? So in a trace-based model, right, the entire experience would be kept and all of the joint information would be kept. So you're not keeping that, but you are assuming you've got the last 400 items.
Yeah. Okay.
Okay, so when you're going through and learning, what you do is you just fill in each of the slots with whatever the last 4 or the last 10 items are. You fill in the context with the counts of the things that were in the last 10, and then you're just counting the number of times those things occur again. Okay, so, and then I'll talk about the probability, how you calculate the probabilities from those counts later on. When you go to generate, what I do is I fill up the first slot. So I actually do this with 10 slots. I fill up the first 6. I generate samples of the remaining 4, and then I generate Gibbs samples of the remaining 4 slots, and then I take the mode of those sequences. Okay, so whatever sequence of the last 4 occurs most often, and that's what I assume is the thing that's generated there. Then I get that and I slide it along. So I say that's what I generated. I'm going to now move things off the end, move these 4 down, open up another 4 slots, generate again for those, and it's just continuing like that. So that's how the model works. So there's lots of precedents in the memory literature for this idea of retrieved context. So the model I was associated with a long time ago, BCD-MEM, worked in this way, but there's also the temporal context model and its derivative, the context maintenance and retrieval model, where there's this assumption that you have items at one level, you have a context at another level, and the items are associated with the context and the context is associated with the items. And there's this kind of loop that goes backwards and forwards between them. But I think we can, some of the work that Kevin's been doing in particular, I think gives us even stronger reasons to think that this retrieved context might be playing a role in language production. So this work revolves around the idea of a paradigmatic association. So if you have words like deep and shallow, they have a paradigmatic relationship to each other. Okay, so in free association, if you give deep, you're likely to get shallow, vice versa. And the assumption has always been that the reason that those would have that paradigmatic relation is because they tend to fill similar slots in sentences. Okay, so I might say the water is deep, or I might say the water is shallow, and it's a consequence of the fact that they fill those similar slots that they're associated. Whereas I'm unlikely to say the water is deep and shallow, right? So the question is, how would that relation be modeled? Like, what is the mechanism by which that relationship is retained? So the one that I have always assumed was happening is that there's a direct association, and this is the old literature assumed the same thing. So the idea is you get the context, you're constantly predicting forward what's going to come next. So I've got the water is, and on one occasion I saw deep, and then it comes to another situation, I see the water is, because I saw deep previously, I'm predicting deep is going to occur. On this particular occasion though, shallow occurs, and therefore there's a sense in which deep and shallow coexist, right? And therefore you could form a direct association between those two things, okay? Because they're both there simultaneously. So that's what I'm going to call the direct association model, and that's what I used in my earlier work on the SP model. Another possibility is that the relationship between these words is coming about as a consequence of representation and similarity. So if you look at something like Word2Vec, you'll also see these words have, well, what you'll see is that these words will come to have similar representations in the hidden name. And so that's because in Word2Vec, you've got the word deep onto a hidden unit pattern onto context, and it's learning that relationship. And because deep and shallow tend to come out with the same contexts, then the hidden unit representations that are created will tend to come together, right? And so they'll tend to be more similar than just written words. So that's another possibility. And then a third possibility is that it's retrieved context. So the idea in retrieved context is that that deep retrieves prior contexts in which it's been presented. And then those contexts then retrieve shallow because they overlap with the prior context that shallow has been presented with. Okay, so the key here, right, is that the first two are encoding models. So they assume that the relationship, that paradigmatic relationship, is being formed as a consequence of what happens at encoding. The retrieve context model assumes that that's happening as a consequence of what happens at retrieval. So what you would expect then, right, is you would expect that if it was the direct association, you would expect that could be formed very quickly, right? Because deep and shallow appear effectively at the same time. And so therefore you could form an association between them. And that association should persist across contexts, right? Because you're forming the association between deep and shallow, not necessarily anything else in that arrangement. The representational similarity account, you would expect that to form slowly and to persist across contexts, right? Because you need lots of examples in order to justify bringing two representations together. You need lots of examples of contexts in which those two representations, those two words have been seen, okay? And so, and typically, you know, in something like Word2Vec, for instance, the learning would be a slow backprop kind of learning. So you'd expect that to form quite slowly, but you'd expect it to persist across contexts. With the retrieve context, though, you would expect that to form quickly because now it's just, you know, as words onto contexts. All of this has been seen simultaneously, and therefore you can form a direct association between those things, right? But because the whole point is that you're retrieving context, if there are other words that are part of the queue as well, i.e. the context, the sentential context that this thing sits in, then they could, and they don't match, right? They're all going to be simultaneously being used to retrieve the context. And so if they haven't been seen, you know, those contextual elements don't overlap, that's going to disrupt the retrieve context. So you'd expect rapid formation, but disruption by new context. So in this study, what Kevin did is he gave people sets of study test sequences. And in the study sequences, he gave them simple sentences like the dog chased Eric, the taxi drove Mary. And then each of those study lists would be followed by a closed test. So the subject would be given the dog chased and they'd have to fill it in. So the correct answer would be Eric. The taxi drove, they have to fill it in. So the correct answer would be Mary. Then on the next occasion, next study test cycle, they were given the same sentences, but now with different fillers. Okay, so you've got the dog chased Henry, the taxi drove Lucy. Again, they're given the closed test, so it's the dog chased. And the correct answer in this case is Henry, because that was the one that was studied in the immediately preceding list. But you can see how now Eric becomes a strong lure, right? Because Eric's been studied in exactly the same sentential context, but just in a different study list from the one that you're supposed to be targeting. And in the static condition in this experiment, that was just repeated over and over again. So you got the dog chased Eric again, you got the dog chased Henry again, and so forth over and over. And there were 12 iterations of the 2 study test list sequences. So 24 study lists altogether. Now, in the dynamic context, what he did is the first 2 lists are the same. So you've got the dog chased Eric, the dog chased Henry, same task. Now, instead of repeating that multiple times, this time the fillers were maintained, but the contexts were changed. Okay, so now we've got the remedy healed Eric and the remedy healed Henry. So same fillers, but different context. But notice the context is still the same from study 3 and study 4. Okay, so what you would expect, right, is that if it was related to the encoding, you should see increased likelihood of Eric and Henry being mixed up, right, because you're getting multiple options where that context is repeated. And then we just had a random baseline. So here it's the context is changing on every trial. So there's actually no basis for the formation of a paradigmatic relationship in the control condition. So what we're going to do, the graph that I'm about to show you, is we're going to look at the probability of producing the paradigmatic associate. Okay, so not how correct they were, but how likely was it that when they're given the dog chased blank, that they produced Henry instead of producing Eric when they should have done that. Okay. And so this is the data, and we've played this out across all of the study test cycles. So the blue line is the static condition. So that's where the context is saying the same and just getting repeated over and over as you go through the list. The orange is the dynamic. So that's where the relationship, the paradigmatic relationship, is being maintained, but the context is changing as you go through the list. And then the green is the random, where there's no basis for a paradigmatic relationship. What we were expecting is we were expecting to see the orange line to look like the blue line. So we were expecting that as you changed the context, because there was, we were assuming there was going to be a direct relationship between the words. And so as you change the context, that direct relationship between the words should be maintained. And therefore you should see this kind of gradual increase in the likelihood of producing those filler items. But that's not what we saw. So what we see, right, is that there is once you've studied with a certain context, and then you study with the same context again, but the different word, there's a very strong probability that, well, pretty strong probability that you're going to produce the paradigmatic filler. But as soon as you change the context, that all goes away. So, and it goes completely to zero. It's basically exactly the same as the baseline. So so it's not, there's not that, doesn't appear to be any sense in which there's a direct association between the two words. And if you look at, so if you think about that in terms of the models I was presenting, we're not seeing persistence across the pairs in the dynamic condition. So that suggests it's not a direct association. We're seeing the paradigmatic related false alarms after just one presentation, right? So if it was the representational similarity that was underpinning this, I would have thought it would take time and it would build, right? That you wouldn't just see it after the very first iteration. But we're seeing it after the very first iteration. And furthermore, it can't be just representational similarity of the items, because if that were the case, they should build over time, right? And we're not seeing that. So the retrieved context seems to be seems to be favored by this data at least, because it proposes that that relationship is formed very rapidly. So that's how it's able to be there on the second list. But it's completely disrupted when the context changes. So
Can I ask a question? Is there a reason why the blue line doesn't keep rising across trials?
Yeah, well, so that's kind of interesting as well, right? So you might have thought that, well, firstly, notice it does tend to be higher in this on the second set than it is for like the first set. Okay, and I think what's happening is it's just the learning is topping out very rapidly. So basically by the time you've got to the second list, or second pair of lists, you've already capped out at the amount of learning that you're going to get. And so that's really interesting as well, right? It's that item under context learning is happening really, really rapidly. Okay, so that's justifies one of the key assumptions of the model. Okay. So I want to talk just briefly about another key assumption of the model, or another key component of the model that I haven't really talked about very much yet, which is how do you go about estimating the probabilities, right? So in order to say generate slot T, I have to calculate the conditional probabilities of all of the different tokens that could be in slot T based on the other items, so the context and the other slots. Okay, so how do I go about doing that? And in particular, how do I do that in a way that isn't subject to catastrophic interference? So first thing to notice about this network, right, is it's not a Bayes net. So you'll see, right, there are cycles in the net, and so in order for it to be a Bayes net, it needs to be acyclic. So this is what's called a dependency network, and one of the advantages of going with the dependency network is that it then makes the training very much easier. Okay, so if you think about if you consider a Bayes net, right? So if you look on the right-hand side, there's a thing called the Markov blanket. And so the Markov blanket is which nodes do you need to take into account when you're trying to figure out the probability of the central node. Okay, so so you need to, in a Bayes net, you need to take into account the parents, you need to take into account the children, but you also need to take into account the parents of the children. Okay, and that's a consequence of these explaining away effects. So the training in a Bayes net is actually quite hard. There's a proof that it's NP hard in complexity theory. So the difference with the dependency network is that the conditional probability of a given node is dependent only on the parents by definition. Okay, and so so that makes it a lot easier to train because you know exactly where the items are. You don't have to pass messages around or anything like that. Now, if it was that easy, why wouldn't everybody do it? So the reason that people prefer the Bayes net over the dependency network is because the dependency network is not guaranteed to give you a consistent joint posterior. Okay, so it's possible to have a set of conditional probabilities within a dependency network for which there is no joint posterior that corresponds to them. Okay, that's why people don't do it. However, Heckerman has argued and demonstrated empirically that if you're training each of your conditional probability estimates on a consistent joint posterior, then they are actually going to conform to that joint posterior, right? So even though it's not guaranteed to happen, as a consequence of the optimization, it's likely that you'll end up in a place that's very close to a consistent posterior. So, so you can, basically, as long as your conditional probability estimates are good, you should be good in terms of creating that estimate. Okay, so how do I construct the Bayes estimators? So what I'm going to propose is that we just use a naive Bayes estimator. Okay, so hopefully not too much math, but essentially what we're saying here is what's the probability of slot I, say in the slots on the bottom, being equal to token K. That's dependent on all of the other slots. So what we're interested in is the conditional probability of slot I equals K given what all of the other slots equal. We can use Bayes' theorem to turn that around. So it's the probability of what all of those other slots equal given the probability, given that slot I equals this times the prior probability of slot I, that slot I equals K. And then the key thing in a naive Bayes estimator is that you then assume independence, conditional independence. And so you can turn that probability of all of those things given the slot I equals K into the multiplication of all of those probabilities. Okay, so the beauty of doing that, right, is that now you can come up with an estimate of that conditional probability based only on the counts of which what items were in each of the slots as you went through the corpus. Okay. So that means learning is counting essentially, which is very fast to train, and it's not subject to catastrophic interference. So what creates that in the other architectures is you get this unlearning of context. Here you never unlearn anything, right? Once a count goes in, it's always in. It does rely on the conditional independence assumption, though. Okay, talk some more about that. This kind of idea using the naive Bayes estimator also underpins a couple of models of memory. So the retrieving effectively from memory model of Schifrin and Stivers, and also the BCD memory model that I generated many years ago. So, okay. So why should I think this would be a good idea? So naive Bayes classifiers learn quickly, as I just said. So this is a classic paper by Young and Jordan, where they looked at discrete classifier performance over a number of different data sets. And they compared a naive Bayes classifier to a logistic regression. Okay. And their observation, so the dark lines are the naive Bayes classifier, the dotted lines are the logistic regression classifier, and M is the number of training examples that the classifier was exposed to. And the y-axis, sorry, is error. Okay, so down is good in this case. And so what you can see, right, is that in every case, the naive Bayes classifier learns much more rapidly. Now, why doesn't everybody use naive Bayes classifiers? Well, if you look in the tails there, you'll notice on several or some occasions at least, it flips, right? So the asymptotic performance is often better for the logistic regression, but the early performance is better for the naive Bayes classifier. And so what's underpinning that, right, is this conditional. So if the conditional independence assumption was correct, then it would be an exact estimate of the correct probability, and it would have to be, the best estimate you could get, right? So what has to be undermining the naive Bayes classifier is the conditional independence assumption. Okay. So what can we do about that? Well, normally when we're talking about training this in a machine learning context, the features are fixed, right? But now we're talking about it in the context of the cognitive system, and it may well be, right, that the cognitive system is designing the features to maximize the conditional independence. Okay. So think about the following example. So let's say we've got words like Boston and San Francisco, and we're trying to predict how likely is it that we'll see the word city in that context. and let's say we've seen the same number of co-occurrences of Boston and city and San Francisco and city. Okay. When we make the conditional independence assumption, what happens is because San and Francisco are two separate tokens, that actually now says, right, that the evidence for city given San Francisco is twice the evidence that it would be for Boston. Right? So it's dramatically overestimating the degree of certainty it should have, because San Francisco occurs, a lot together, and therefore this is a situation where the conditional independence assumption is broken. Okay. So what can you do about that? Well, you can combine features, and we'll be doing that. And you can also weight the regression equation, and we'll do that as well. Okay, I'm going to skip through a whole bunch of slides here, just to quite quickly, but let me just quickly say, so the first thing we do, right, is instead of just taking the words or the tokens as they appear, we combine sets of tokens that are high frequency. Okay, so was-are is seen often. So instead of being two tokens, it's now one token. Okay, same with of the first. The other thing, I'm going to completely skip over this bit, but there's a lot of interesting stuff there. The other thing is the weighting function. So I won't go through this in detail, but what we can do, right, is instead of just saying we're going to take those probabilities as are, we can say let's weight the degree to which the probabilities from a certain slot to another slot are influencing the conditional probability, and then we can optimize those. And so that's what I'm doing. Okay, so a bunch of other stuff here, but I'll skip over all of that and just finish with a couple of example generations. So I kind of got caught a little bit short in terms of getting the data out. This is on a small corpus, so 150,000 words. So think about that in the context of 43 trillion words. 100 GIB samples for each generation. And what I've done here is the text that you see in bold is what I entered into the model, and then everything else is what the model has generated subsequently. Okay, so you can see April always begins on the same day of the week as July, and additionally January in leap years. April always ends on the same day of the week as July. So just to so you can be assured it's not just replicating what's in the corpus. So July is actually wrong. So the answer should be December there. And the corpus actually says it's December, but the model's getting it incorrect.
Is this a natural corpus or a specific corpus to look at?
This is the simple wiki corpus. So it's so it's Wikipedia, but it's the one that's generated to be friendly to non-native English speakers. So you can see, it's generating a lot of coherent stuff. That's probably the best example, that first one, but an idiom is a common word or phrase which means something different from its literal meaning. You can see it starts to fall apart at the end there. So because idioms can mean what the words mean, it is difficult for, so it starts to mess up at the end. I think what it's trying to get at there at the end is that idioms are difficult for second language learners to capture. So in the 20th century, some countries research on the bacteria, the bubonic plague, some common form of the disease, which is spread by a certain kind of flea on rats. So certainly not perfect, not GDP level yet. People have asked themselves if God exists, and that's the answer to that. So clearly, not at the same level as GDP yet, but it's getting a lot of stuff right? It's getting a lot of coherent sequences, even when it's missing in terms of local structure. The words that it's choosing are kind of words that are relevant to that particular context, right? And that's because it's doing this context retrieval thing, right? So it's doing okay. And there's a lot to go yet. So all of the contexts, I only had the with 10 contexts. So I think some of these problems with the way it's not filling in stuff at the end might be addressed as I increase the context lengths. So some conclusions. So I think transformer models are really interesting. I think they're transformative in that they demonstrate the viability of acquiring control and representation from image input. However, they learn too slowly, they forget too quickly, and the mechanism by which they ensure the global optimality from local interaction is implausible. So what we've done is presented a retrieved context account of sequence generation that avoids those deficiencies. The paradigmatic relationships, the experiment that I presented of Kevin's, I think favors this kind of retrieved context idea. And I guess what I didn't get to talk a lot about was, I think what the system is doing is it's settling on a naive Bayes classifier as the thing which does the generation. And then what the kind of input feature creation system is then designed to make sure that the features are such that they're you're not getting violent violations of the conditional independence assumptions. And so, what I'm kind of terming that, it's the system's trying to operate on the edge of independence, essentially. And that then means that the learning becomes easy if you do that. And that is it. Thanks very much.
We have 5 minutes. There is somebody in this room afterwards, so we'll have to vacate it. We could have time for probably one question. I've got a question.
Okay.
So another issue which showed up in the examples of GPT-3 when it was responding to kind of the Turing test questions was that the grammar and syntax were really good, but the content was really mediocre. It was, responding at the level of like an 8-year-old child. Is that just a function of the corpus that it's trained on? Like, if you ask it, why do animals only have 3 legs? It doesn't reference genetics or anything like that. It has a kind of silly sort of answer.
Oh, I see. Well, yeah. I mean, I suspect, right, if you ask the majority of people, that's the kind of answer you get, in fact.
But animals can have 3 legs, right?
Well, sure, but I still suspect if you ask people, mostly they would say they don't have 3 legs.
Oh, sorry.
So, and it's absolutely dependent on the corpus, right? So
Okay.
if there was I'm sure if you had like a genetic, a corpus that had a lot more information about the relevant genetics and so forth.
One of the things I saw on Twitter that was a lot more problematic was it could contradict itself.
Yeah.
Like through a series of questions, like you could literally kind of re-reference a similar question before and give a totally different answer.
Yeah. So it's cohesion. So I'm running this project at the moment where we're trying to simulate clients who have some kind of mental health difficulty as a training mechanism for new clinicians. And so we've been generating these conversations. And so first thing to say is it does really well. Like it's, the clinicians we've talked to say, oh yeah, that's pretty close. But we do see this kind of stuff, right, where it gets stuff wrong. And it kind of it contradicts itself. And one of the things that we've been doing to alleviate that is so when you have the prompt, if you put more information in there about the context, so we've been putting in things like, names of siblings and kinds of, medications that people have been exposed to and things, that are taking and so forth. And when you do that, some of that stuff goes away. So it seems like it gets too, if it doesn't have a context which is specific, then it wanders.
Yeah, but I'm just curious as to how that's happening. Like, does it contradict itself because it starts to kind of tap into different knowledge from the corpus, or?
So In the transformer model, it has a fixed context,
Mhm.
right? So so the longest ones will go back like 1,000 tokens.
Okay.
And it really doesn't, it's not training, there's no learning that's happening
Yeah.
outside of that for an individual context, for an individual conversation. And so if something falls off the end, it's as if it never knew anything about it.
Right.
So yeah, so I think that's why it has that kind of problem. And that's also a key problem, right? So because clearly that wouldn't happen with people, but I think that's because they're actually doing some learning as they go along.
Okay, great. Thanks, Simon.
Cool, thank you.